So I'm Melissa, Max, and Hayun. We're gonna talk about some acrobatics that we're gonna have Atlas perform for y'all. So this is our presentation roadmap. We're gonna go over some objectives, the overall problem that we're trying to solve, our results, how we generated trajectories for our simplified Atlas model, how we optimize those trajectories, how we tried to simplify our constraints, and then our implementation of MPC and whole body impulse control. So just to remind y'all, this is what we were shooting for. A jump, a spin, a backflip. There you go. So we're gonna go into our problem overview.
All right. So, yeah, quick recap, I guess. So the problems we're focused on, to narrow the scope in a little bit, are acrobatic motions with these 4 phases. And essentially, it's always going to be, it's the contact schedule is what's said. It's always going to be a ground phase, and then there's a flight phase, and then there's a landing. That can be jumping on a box. That can be jumping and doing a twist. That can be doing a backflip. Those things are configurable, but the contact schedule is what is essentially like set between the different problems we're trying to solve. So with that in mind, the general pipeline for solving this kind of problem from the literature, from what we can tell, is there's 4 steps. And the first thing is to generate a reference motion from simplified models and the contact schedule. So things like the centroidal model, are going to give you, what we want our center mass to be about here at this time. The second step is you feed those references in to an offline trajectory optimization, and that uses centroidal dynamics and whole body kinematics. So yeah, we have 4 stages in our pipeline. We generate reference motions. We feed that into an offline trajectory optimizer that uses centroidal dynamics and whole body kinematics, and that produces kinematically feasible motions and motions that satisfy the centroidal dynamics, which are typically a pretty good approximation. And so once those are done, we can use those as a reference for an online controller, which would be a Model-Predictive controller, and that improves the trajectory tracking, and that feeds into the whole body impulse controller. What was that? Okay, so next we're going to talk about some of the results. I will go ahead and tell you it's a very difficult problem to make a robot do a backflip. Some parts are easy and some parts are very hard. So we have a couple videos. The gist is the linear momentum, like the jumping actions, they're not super difficult for someone who's taking the class. The angular momentum parts are very hard for a lot of reasons, and also just because it's easy to regulate your angular momentum to 0, even if it's like really nonlinear, but to actually like prescribe that we want to turn is a much harder problem to actually do in an optimizer. So also, like, how many robots in the world are doing backflips regularly? So there's a lot of like open space there. So we have a couple different jumping motions, and these are highly configurable to the point to where you can basically just select the initial and final poses and it will work itself out. So
these are the final results after the whole pipeline.
So this is animations of the trajectory output. This is not simulated, to be clear.
This is so you have the trajectory generation, the trajectory optimization, the MPC. Which one is this one?
This is after the trajectory optimization. So this would feed into the MPC. Okay. So it is kinematically feasible and has the centroidal dynamics, but it's not simulated like pi PNC has joint friction and all kinds of stuff like that. So this is the idealized model. Right. Yeah.
I mean, one thing I don't know if you recall that the first time I saw Atlas doing the kind of the gym stuff a couple of years ago, the first gym, not the latest one, right? It was jumping on boxes, and it was jumping in one of them that looked like a human because it jumped and it almost looked like it kind of floated in the air. The legs for a moment, they were kind of floating at a distance. It was like kind of funny physics, except that they were the real robot doing the funny physics, right? And I see a little bit of this funny physics on the right video.
It is. It's
humans don't sort of let the legs there sort of stiff and then kind of looks almost like a space trajectory, right?
Yeah,
but it is, but the robot doesn't, you know.
it's more evident in this next video, actually, I think. How do I go to the next slide? Come on. This was something I noticed last night because for a while I thought it was a bug, but I looked at it and it just is like, what happens? Yeah, you can, we'll talk about it more, but like at the places where your phases kind of, they change where the hybridynamics are, it's hard to solve those. And so there's just some interesting like behaviors that emerge there.
Another question, why so dark?
Why so dark? That's just the default RViz. Oh, because you have to work late at night. That's why it's so dark and it hurts your eyes.
Really?
I don't know. That's just what RViz looks like. Next time we'll brighten the videos up. Yeah. So again, those are configurable. You can change those without really too much difficulty. Yeah. So that's the general overall results. Melissa's going to talk about our reference generation.
Okay. So this is a slide that we've had from our other progress updates, but just to reiterate, this is how we got our center of mass trajectories. We supply a given start and end position of the center of mass. We use a projectile motion equation to get this trajectory. This is for doing a backflip. You can see it rotates about like the y-axis. So from this, we can get takeoff and landing velocities from our desired position trajectory, and then we can estimate reaction forces from that. So
Is the orientation, right?
yeah,
Yes.
yeah,
Okay.
yeah. And then these are the
Those
feet.
are written by hand, right?
They're generated like
We,
Do you these keyframes, do you
no, it's
describe them by hand?
you'll see it
It-
in a second.
the only thing we give it is like the XYZ position of the center of mass.
Oh, okay,
Yeah,
all right.
Those aren't specific
So you
keyframes.
have-
It's
you have
just
an idea of completing a full 360 rotation, and that gives you the
Yeah.
orientation.
that's just sampling from the trajectory
Okay, all
for
right,
visualization.
great, sounds great.
yeah. Okay, and then, so to give it some kind of idea of what kind of posture we want it to have during the wind up and landing phase, we calculated these two postures. This one is standing high and this one is standing low. And then we interpolated between these two to get like a smooth transition. So that was just for smooth movement during the wind up and landing phases. The more interesting trajectory, the angular momentum trajectory, we started with a desired orientation of 0, 0, 0 for a backflip, and then a desired end orientation. And you can see our trajectories linearly increasing to 2 pi for the pitch. And then from there, we calculate an angular momentum trajectory. For our implementation, we assumed constant inertia. So that's obviously something that's not feasible for like a really good backflip. So our future work includes calculating inertia for different configurations that's not just like standing high and standing low. So yeah.
Although in real, gymnastics, right? People, when they do it, I think they change the feet, the crouching when they turn. So probably the angular rotation, there's an acceleration and deceleration. It's not constant velocity.
Yeah.
So it could be interesting to compare anyway.
Yeah.
In the future with real people.
Yeah.
Oh yeah, trajectory observation. That's
Or
me.
you can record one of you doing a backflip.
I looked at YouTube videos for a while. Yeah, so next up, we're going to talk about the trajectory optimization. Great, so don't worry, there's a lot of slides on trajectory optimization. A really important reference for us was this paper, An Introduction to Trajectory Optimization, How to Do Your Own Direct Collocation. And it's like a 50-page, basically like ground up tutorial on how to do these kind of methods. It's by Matthew Kelly. He finished his PhD in how he works at Boston Dynamics on trajectory generation for Atlas. So that went well for him. Anyway, we reference this a lot, so I like to bring it up. We're focusing on direct transcription. And so we're taking like a continuous problem and we're approximating it as like a finite size nonlinear program. And then when you convert it into that mathematical formulation, you're able to use, solvers that have existed for years and years because it's a general problem. Specifically for trajectory optimization, though, there are things you have to consider when you do that approximation. So the discretization, we call them knot points. I know you guys have heard it many times. The dynamics and the constraints are only enforced at the knot points in the NLP. And so when we get a result out of it, I guess I can't, yeah, I gotta be on camera. When we get a result out of it, we essentially want to interpolate between those knot points to kind of recover the continuous solution. And you can see already, depending on like the time step, you can have varying results. Depending on if you use a linear interpolation or if you're able to use, a cubic or a higher order polynomial, you can get varying results. So that's something to keep in mind. And there's a lot of different factors that play into that in designing the optimization. Being able to recover the continuous solution, though, is very important if you want to be able to like subsample it with an MPC. An MPC is going to run at a lot higher frequency than these. Our optimizations mostly ran at 100 millisecond knot points, and we could send them down to 10 milliseconds, but it would take quite a while to solve. Yeah, so these are actually some of our results. Some of the interpolation methods, I think this is jumping on the box. And so you can see, so first off, we have references, which are like these little dots here. Oops, go back. So there's the original reference, and then the black dots that like line up with the spline is the output of the trajectory optimizer. You can see there is linear interpolation and cubic interpolation plotted on all of these. And so in some places they agree perfectly, and that's great. And in other spots, they start to diverge, and you can tell that's a spot where you could use more knot points. They're both approximations, so they're never going to get the true solution, but the closer they converge together, the more likely that it's correct. You can particularly see in the angular momentum, because the knot points are sparse. So for example, in the takeoff and landing phases, you only get about 3 time steps because they're really quick. That approximation degrades a little bit. And so this is a couple future work questions. A couple open questions are you solve it with 1 time step, you interpolate it, you sample it, use that as a reference for the same optimization with a much higher time step. And that is, we'll talk about it in a minute, but the initial guess is absolutely crucial for this kind of problem. So being able to, solve easier problems and work your way up is really important for the sake of time and for the sake of convergence. So yeah, some other things would be incorporating, like there's ways to do variable knot points, obviously. So if there's poor convergence here, you can just add more knot points just in that one spot. And yeah, quantifying the error by looking at those 2 solutions is another thing that can be done to analyze how well your NLP is actually approximating the true solution. We won't get too dirty in the math, but the general formulation of ours is we have a quadratic cost function that's just every state variable versus all the references. Because it's a trajectory generation problem, the state variables include all of the joint positions, all of the joint velocities, the center of mass, position, velocity, and acceleration, the angular momentum, the rate of change of angular momentum, the contacts, and the forces, the whole thing. And so you can imagine if you take that 87-degree thing and stretch it out over a bunch of time steps, the dimension just explodes. So even for a 100 millisecond time step, we have 1,200 variables that we're solving. A huge thing that is difficult, and the reason we don't have like twisting motions today is the angular momentum is really nonlinear, and it's really non-convex, and it makes it very difficult to solve that. The joint kinematic constraints actually solve pretty easily despite being nonlinear. But yeah, there's those couple of factors are what takes us from a problem that's easy to a problem that's like really difficult. So another thing that we talked about in past presentations is that we're doing multi-phase trajectory generation. And what that means in this context is we have hybrid dynamics, we have different contact schedules. And so the constraints effectively change in different parts of the optimization. Because we have pre-specified contact like durations, we can do that. We can just change, you just change these constraints. It's all math, and that's okay. But there are interesting things that go along with that. Again, interesting enough, the majority of the constraints apply to the entire trajectory. Euler integration enforces continuity between states, like, positions. The Centroidal Dynamics applies the whole time. Joint kinematics applies the whole time. The only thing that really is in this problem that switches is those contact forces. So yeah, for example, in this period, you enforce that the contacts are just always in the same spot. The forces have to obey friction cone, ZMP or ridge cone constraints, that kind of stuff. In the air, this is from the original paper, they enforce that the constraint, so the contacts are really the end effector locations. So in the air, they enforce that the feet have to be above the ground. For time's sake and because of the easy terrains, we just left that out. But that's another thing to keep in mind there. So we were very optimistic about multi-phase trajectory generation in the beginning. We thought this is going to be cool. It's going to add a lot of flexibility at these transitions. Instead of having to stitch these phases together and have like very strict intermediate spots, you can let the optimizer do its thing. We were also thinking, basically separate the idea of a keyframe from a knot point. We could have 1,000 knot points and then pick 10 or so keyframes and weight those really highly, or even constrain them to guide the optimization through that. And with that like kind of philosophy, you can see like cool emergent behaviors because you're giving it a lot of flexibility. You can see, it figures out that it needs to move its arms in a certain way. The negatives we found in the long run, not necessarily this isn't a thing to do, but to keep in mind is it's a lot faster to solve 4 tiny problems than it is 1 big problem. If you saw Jamin's dissertation, he specifically says it's like 10 or 15 times faster. So that's something that is important to keep in mind as a trade-off. Another thing, so we'll talk about the optimization methods in a second, but typical like gradient-based optimization produces like locally optimal solutions. Getting a globally optimal solution to a nonlinear problem, a non-convex problem, is significantly harder. It takes a lot longer. So if you actually give it too much freedom in this non-convex formulation, it doesn't converge or it takes forever, and it's very problematic. It can find little tiny minima that barely even exist and get stuck there. A lot of the times, especially for these stuff like the contacts where it's just specified all the time or it doesn't matter, you'll find like really shallow valleys where even if you can optimize this way, I can say, oh, go this way until you get lower, but your solver will get stuck there for a very long time because it's just moving at a very slow rate. Okay, some of the solver characteristics. Yeah, convergence to local minima. That basically means that the initial guess is really, really important for this.
So the F min con is the solver that you use.
F min con is the solver that we use. It's in MATLAB. It has a couple different options. Specifically, we use the interior point methods. We tried SQP and it did not scale. Similarly, like SNOPT uses sequential SQP methods, but it's meant to handle really large sparse problems. The interior point methods, something like IPOpt, that's what we're using. I guess it handles sparsity better, so if min con just happen to have it.
You solve it for 5 minutes. So you solve it for the entire jump trajectory.
Mm-hmm.
But you talked before that you solve it in chunks of 100 milliseconds. I didn't understand.
So it's not that we solve the chunks of 100 milliseconds. It's that the knot points are spaced by 100 milliseconds. Okay. Yeah. There are a couple times that we solve it in chunks. 5 minutes was the total. So like, I think that one we solved a 3-minute chunk without angular momentum and then a 2-minute chunk with it. And that it depends. It's really highly variable on like the initial conditions and the trajectories and the references.
Running on a laptop.
That's running on my desktop computer. So okay. There's also a number.
That's pretty fast.
There's a number of things we did to speed it up. Originally, it took a very long time. Here, that's what's on the slide. Let's see. So yeah, the gradients and the Hessians are extremely sparse, like literally like 99 or even like empty most of the time. So taking advantage of that is something we haven't done that we could do. We did spend a lot of time. We basically developed our own forward kinematics for Atlas. We spent like a while doing that. And so we had analytical gradients and Hessians for everything. And that gave like a 1,000 times speed up. Because when you don't have those, it has to calculate them with finite difference methods. You can use parallelization and it will speed up a lot too. But if you take one thing away about trajectory optimization, really please get some gradients and like have them available. Yeah. A couple more things. When you get into the meat of it, it gets tricky because the way IP interior point methods work is they treat constraints as like barrier functions, and they have like this logarithmic slack. The point is they're kind of like really, really high costs and not hard constraints. So if you can't start off in a feasible spot, it can be counterintuitive to have your objective you're trying to optimize and also be trying to become feasible. Sometimes we remove the objective and just solved it to a feasible point and then added it back. There's a lot of little things. Normalizing the variables is also important. We basically use, if you remember Bryson's rule from like LQR, we basically did that where you take, a joint, angle should not be more than like 0.1 radians or something, and you can kind of smooth those out a little bit. Okay, we're getting through the thick of it. So some of the big challenges, nonlinearity and non-convexity cause poor convergence and getting stuck at local minima. Transcribing the formulation into code has a really high chance of introducing bugs. Implementing this is literally taking that math slide and putting it in MATLAB. It sounds, just do it. It's so difficult to debug something like this. Long stall times make small mistakes costly, and the high dimension makes it very difficult to visualize it. And so these are our solutions to these problems. So we've already talked a little bit about solving simpler problems, adding constraints step by step. We've said it's really important to have analytical solutions. There's also analytical differentiation, is just a bunch of softwares where through the magical power of math and algorithms, they will figure out, basically your gradients and your Hessians from just the base thing. You don't have to like take those. So that's a very powerful tool. Yeah, a lot of ways to speed it up. The big thing I want to get into is something when we realized we probably weren't going to be able to do a lot of like angular momentum motions in the time we had, we kind of pivoted into how can we understand these problems better and like see what's going on. Because if you've debugged something complicated in your life, you probably know that visualizing it just changes the game. So we actually wrote up this kind of animation thing that works in with a trajectory optimizer. And so at every iteration or at like a specified number, it shows what the trajectory looks like. So this is what the jump looks like, and you can see it converge. And the thing that I'm really excited about, because I haven't seen this anywhere else, is, so we said that the constraints they're not always feasible and they're not always satisfied. This is actually plotting all of those, like some of those constraints, where you can plot like the knot points over time, and you can plot what the variable is. And you can see like, okay, in these high blue spots, that's where our Euler integration like doesn't work. Like our velocity and our position are not agreeing. And as this thing runs over time, it shrinks down because that shows you that it's getting better. Some other stuff is keeping the ankles flat on the ground. There's some more interest. The nonlinear ones are a little bit more interesting, but couldn't get them to shrink all the way down. So, but yeah, this was a very crucial. The moment we got this working, we immediately fixed like 10 bugs, and everything just sped up dramatically. So focusing on tools and process is a big thing for stuff like this. So yeah. Cool. Are you done? You can see down here, the feasibility is, this is essentially the amount that all the constraints violate. And so it's really more of a feasibility problem than an optimality problem at this point. If we already had a trajectory that could walk over there and do that thing, we could probably just use it. Like, we don't care that much if it's a little bit off, but actually getting something that works is difficult. All right, video, you're done. Okay, thank you for listening. Go take it on, Melissa.
Okay, so to give our optimizer a little bit of an easier time, we tried to simplify our nonlinear constraints, mainly the angular momentum constraint shown here. This is from a paper by Oren. It basically, you can think of ACAM as like the I and Q dot as like omega. What this does is it takes the inertias of all your links and transforms them into your center of mass. So you have this constraint for the angular momentum of the center of mass. So yeah, this ACAM matrix is the nonlinear part. It has a lot of transforms. So what we tried to do was to simplify this ACAM matrix, we saw that a lot of the robot's mass was concentrated around the center of mass. So we decided to reduce the number of joints that was needed for the ACAM matrix. We got rid of the neck, the wrists, and the ankles. You can see that they're pretty small. So yeah, this is the performance of that. These two histograms plot the error in the center of mass positions and the error in the simplified versus the whole joint configuration ACAM matrix. You can see that the error is on a scale of like 0.5 millimeters. And this is over 50,000 random joint configurations. And yeah, this ACAM error is around 0.05 kilograms meters squared per radians. And to give you like some perspective on what kind of magnitude that is, if you have a robot that like rotates around its z-axis, the angular momentum is around like 50 kilograms meters squared per second. So this is pretty small. We didn't have time to implement this. So future work would just be using this simplified ACAM matrix versus the whole joint configuration ACAM matrix.
So when you simplify it, it's linear, right? You made it linear or just loops?
We set the joint rates of the joints we didn't want to include to 0. And then we multiplied it. And then we just enforce this constraint, or we enforce the new ACAM matrix.
It's still nonlinear, but the computational complexity decreases a lot. It actually takes like, to analyze the Hessian of that takes like 40 seconds. There's a lot of simplifications to make, but there's two parts in making it faster to compute and also making it, it's still mostly nonlinear. But it also helps with, if your optimizer is sitting here twirling your wrists all day long, like it's not doing anything, it's just wasting time. And it's wasting, it takes steps in certain directions. So having like almost dummy variables in there is not productive.
So,
All right.
was that?
Yep. So after getting the optimized trajectory, the next steps will be inserted into different controllers. Here we apply two of them. One is Model-Predictive control, and the other one is whole body impulsive control. The purpose of applying Model-Predictive control is basically to follow the desired trajectory as much as possible, especially the orientation and the position of the center of mass, and of course the velocity of that, while considering trying to decrease the ground reaction force as much as possible, especially the one around X and Y axis. So what do we have here? It's basically this set of formula. This X is defined as the objects variables that we're trying to make it follow the trajectory as much as possible. Theta is the Euler angles of the body. P is the position of center of mass. Omega is the angular velocity in the world frame, and the P is the positional velocity of center of mass. And these are the constraints that is being provided that will supposed to be inserted into the Model-Predictive controller. And this is the Model-Predictive controller, which is a quadratic programming optimization problem that we're trying to solve. Here we set the time horizon as 10, and the time step for them is 0.005. The reason to do that is because the landing phase, the time of landing phase, basically too short. It's only about 0.2 seconds, and the original interpretation don't have enough resolution for that. And to solve this problem, I tried to. Oh, sorry. Yeah, there are several things worth being mentioned, and the first is about the time horizon. It's set as 10 with a resolution of 0.005. And the other thing is because of the landing time is very short, and it's only have very little knot point. We were trying to like doing some further interpretation of this 0.2 seconds. And subsampling and the interpretation is one thing we tried. The cubic interpolation is applied for most of the variables, including the x, including the position, velocity, angular, and the orientation, except the rotational matrix, because that one cannot be realized through cubic interpolation. And we use spherical linear interpolation to solve this problem. We basically convert the rotational matrix into the quaternion and do the interpolation using the slurp, and then transfer it back to rotational matrix. The purpose of applying rotational matrix here is to because it is part of the constraint formula. And yes, yeah, and
so the cost in the reference is the orientation trajectory.
The reference is the orientation of the body, the position of center of mass. Yeah. And because in the previous section, there are different variables that can be set to the quadratic programming optimizer. And here I tried some options because there's no reference given on the paper about like which value should be set into it. Here I defined Q as weight 1 and R as weight 2. One of the options I tried is set the weight 1 to be 2, the other one to be 0.5, and the other one is 1 versus 0.5. And here I picked several examples after the quadratic optimization. There's a typo here. The red one is the reference. And the
We're simple, right?
sorry, yeah, that's
straight line.
yeah, that's a typo. The red line is the reference. The blue line is the predicted value through the model-predictive control. The result is not perfect, but in general, the predicted value will converge to the set value. This is the one for the position of the center of mass. And this one is for the omega, which is the angular velocity in the world frame for all three cases.
Why did you choose 2 and 0.5? This is the two-dimensional. Well, you have. It's not two-dimensional, right? Because you have x is 4-dimensional, right?
X is that's 3 times 4. There are 12 values in it. Okay. Because each element has a 3-dimensional one, and there are 4 of them, so there are 12. So essentially the R and the Q and R are set as identical matrix times the value of weight. So the W1 is for R equals to W1 times identical.
Okay, one is Q.
Yeah, one is for Q. Yeah, the other is for. Okay, yeah, sorry, that's I didn't specify this part here. Okay. But so yeah, basically they are inserted into different identical matrix.
Understood.
And these two, this graph is for the ground reaction force. The ground reaction force is not supposed to tracking a reference, because the reference is basically for the values related to center of mass and the orientation. The purpose of having ground reaction force here is trying to minimize it or let it converge to a stable value, so it will decrease the chance of the robots falling, because the model-predictive control is designed for the landing phase.
Your trajectory optimization, does it speed out ground reaction forces?
Yes.
And those are provided to the MPC?
No. The ground reaction force is simply supposed to be minimized. It does not compare to a reference one. The result here is not very ideal. Theoretically, we will expect the ground reaction force in the X and Y axis converge to 0 as much as possible, and the value on the Z axis will like.
How can it be so small? Like 10 to the -3 what, like newtons or what?
Um,
So it's more, right?
yeah.
Maybe.
I can't remember the specific value, but I think it should be kilogram or something. But yeah, it does not make sense. Maybe there's a problem of
maybe you have
the
a scaling
normal.
problem or something.
Yeah, I think maybe the normalization is not
Oh,
done
it's a normalization.
it's not done correctly, so this value looks very small. But yeah, so the result here is kind of preliminary. We're still trying to find out what is the reason that does not make this looks really good. And at the same time, the resolution of this one is not still high enough. We only picked like 8 sampling point out of this. Next time we have a chance to
But
follow
the trend makes sense because it's landing.
Yeah.
So it goes, which one is the Z component?
This one.
So you're landing, so when you land, I mean, you should have like a peak and then, because you have the
Yes.
impact, right? So you
Yeah.
should have like a thumb.
Yeah, it should
And
go down later.
Yeah.
I think the time horizon of the landing is small enough that it looks more like your feet like touch the ground and then you apply.
Right, yeah, if you crouch a lot, then maybe it's probably constant. Maybe.
Yeah, going back to earlier when we talked about how it like the feet thing.
Yeah.
We are enforcing the first contact is enforced with like, it might even be a 0 force. It's just put your feet there. So it's a very like smooth.
Yeah.
Anyway.
Yeah. All right.
So after we have the model predictive control result, it basically tells the robots the orientation and the center of mass, position, velocity, this stuff that should be realized by the WBIC, and of course as well as the ground reaction force. So oh sorry, yeah, I think maybe there's a typo here. This is just another ground reaction force result. So the ground reaction force part is not perfectly down. We are still suffering some kind of bug along with the programming. But basically, what the ground reaction, basically the whole body impulse control trying to do is to like prioritize the task provided by the MPC into different level. And here we should define the body inclination as the priority, as the first task, and the centroidal momentum as the second one, and the trajectory of center of mass as the third one. We tried a lot to realize it in PyPNC, but to be honest, I think my programming skill is still kind of rusty, so I didn't crack this part, so we cannot see how the trajectory tracking will looks like after we apply the WBIC. So yeah, this is something I didn't do well. Yeah.
Okay, thank you for listening. Thank you.